Jia En. Okay, good afternoon. Okay, this session is specifically for you. Okay, 4th April 2026. Okay, so we will continue from where we stopped. Okay, the last lesson. Okay, so we stop at exercise 5, problem 3. Okay. Okay, let me shift the timer to bottom left hand corner first. Okay, so okay, so this is where we stop at exercise 5, problem 3. Okay, so let us begin by reading the question. Okay, a square piece of tin of side 12 cm is to be made into a box without a lid by cutting a square from each corner and folding up the flaps to form the sides. What should be the side of the square to be cut off so that the volume of the box is maximum? Also, find this maximum volume. Okay, so because it's a word problem and I mentioned before, okay, it will be good to take note of the keywords. Okay, so the first thing you should take note, this 12 cm, okay, is actually the side. Okay, and take note that this is a square, which means all sides are congruent. Okay, the top, bottom, and the side. Okay, the two sides. Okay. Okay, the second keyword is this statement. Okay, cutting a square from each corner and folding up the flaps from the sides. Okay. Okay, and next thing they ask you, right? The question here is, what should be the side of the square to be cut off so that the volume of the box is maximum? Okay, so since the question is this, right? Okay, what should be the side of the square to be cut off? Correct. So we will define our side of the square to be cut off, okay, to be x cm. Okay. Okay, so denote the side of the square to be cut off to be x cm, because this is what we want to find, our objective. Okay, I will go here. Okay, the question asks you what should be the side of the square to be cut off, okay, so that the volume is maximized, okay, or maximum. Okay, so we will let the side of the square to be cut off to be x cm. Okay, and then since we want the side to be cut off, okay, meaning the length and the width, which means, and the initial length is 12 cm, correct? So the length to be cut off will be 12 minus x, 12 minus x. Okay, so, and because square has congruent length, correct or not? So the 12, okay, ideally you can combine, so become 12 minus x minus x. Why minus x 2 times? I think this was a debate follow from the last session. Correct? Why you minus twice? Okay, because a square has two sides that are congruent. Okay, the top and the bottom as well as the side. Correct? And because I want to cut off the side of the square, correct? Okay, at the corner. So which means this part, okay, which is 12, right? Correct? So assuming, okay, I take half of it, let's say x, okay, and the other side, okay, which is 12, I take half of it, which is x. Okay, so in total we have what? 12 minus x, right? Okay, from the corner. Okay, that's why you have, okay, minus x here, hence is minus 2x. Okay, and because square has congruent sides, so 12 minus 2x is actually the length for, okay, the length and the width, okay, or rather the dimension. Okay, 12 minus 2x is the dimension for the length and the width respectively. So hence the volume of the box is length times breadth times height. So 12 minus 2x times 12 minus 2x times x, which is 12 minus 2x times to the power of 2 times x. Okay, so this is the expression. Okay, can I will say, okay, take some time to digest, okay, why, okay, the expression of the volume of the box is like that. Okay, especially, okay, the minus 2x portion. Okay, and you may ask, how come the height of the box is x? Okay, because, okay, we only want to know the side of the square to be cut off. So the side of the square here refers to the length and the width. Okay, where the height, okay, there's no change. Okay, it's invariant. Okay. Okay, or you just assume, okay, volume of square, okay, or cube is basically what? Length times length times length, which is L cube. Correct? And here, okay, our variable is what? X times x times x, x cube. Okay, but the initial length of the side given to you is 12 cm. Okay, and we cut off, okay, from each of the corner, folding up the flap to form the sides. Meaning, Okay, your initial length 12, you need to minus off x, okay, from the length and minus off x from the width. Hence, we have 12 minus x, which is 12 minus 2x. Okay, this is how you get the expression for the side, okay, or the dimension of the length, okay, or the width. Okay, and because square has congruent side, that is why 12 minus 2x, okay, there's a power 2 here. Okay, so one is the length, the other one is the width. Okay, and then once we have this, okay, in order to find out, okay, the volume of the box is at its maximum, we use calculus, meaning differentiate the volume with respect to x. So okay, we have dv over dx, okay, or v prime x. Okay, and here take note, it should be product rule, because we have two terms. The first term is x, the second term is 12 minus 2x squared. So using our product rule, differentiating x with respect to x, there is 1. Then you keep the second term plus keep the first term, which is x, differentiate the second term. So the second term is 12 minus 2x squared, right? You bring down the power 2, inside the bracket remain the same, and then differentiate the term inside the bracket, which is negative 2x. You differentiate that with respect to x, you get negative 2. Okay, 12 will be 0 because 12 is a constant. Okay, then simplify, okay, and noting that since this term has 12 minus 2x squared, okay, and this term has 12 minus 2x, right, we can factorize out, okay, the common term with the lower degree, that is 12 minus 2x to the power 1. Okay, so you take it out, you have this. Then, okay, you still left one more term of 12 minus 2x, right? Okay, you put it back. Then for the second part, since I already factorized out 12 minus 2x, right, the remaining term is 2 times minus 2 times x, that is minus 4x. Okay, then you simplify the terms inside the square bracket, okay, that will give you 12 minus 6x. Okay, then of course you still have the 12 minus 2x in front. Okay, so this is the dv dx expression. Okay, and what's the next step? Okay, after you differentiate, you need to find the stationary point or stationary value. So to do that, okay, for stationary point or for stationary value, okay, we require dv over dx to be 0, equal to 0. Okay, so you equate to 0, and then this implies that either 12 minus 2x equals to 0 or 12 minus 6 equals to 0. So if 12 minus 2x equals to 0, x will be 6. If 12 minus 6 equals to 0, x will be 2. Okay, so here we notice that there's two stationary points. However, okay, we should not take both values. Okay, why? Because if you take one of the value, you substitute back into the volume of the box, you realize that you get 0. So what does 0 means? It simply means that the length and the width is 0, which is not possible. Correct? Okay, so okay, I put here, note that x cannot be equal to 6 since the length will be equal to the breadth and it becomes 0. Okay, so this is what I mean. Okay, so our volume of box expression is x times 12 minus 2x squared, right? So you substitute x equals to 6, you get 0. Okay, so this means that, okay, volume equal to 0 means that the length and the breadth are equal. Okay, hence we get 0, which is not possible, correct? For the length and width to be kosong, okay, or 0. Hence, the other stationary point value, which is x equals to 2, must be the answer. In fact, you take s equals to 2, you substitute into the volume of the box, okay, the answer will be non-zero. Okay, then after that, once you differentiate, okay, get your dv dx, you set to the 0, find your stationary point. What's the next thing? Okay, use either first or second derivative test to show that the box is maximized, okay, or the box is at its maximum when x equals to 2. Okay, so for the sake of learning purpose, I actually include both the first and second derivative test in problem 3 to problem 5. Okay, but in the class, okay, I actually used first derivative test to explain to Charlene. Okay, so up to you. Okay, you can, like what I mentioned before, okay, it's your own preference whether to use second derivative test or first derivative test. Okay, it's your preference. Okay, so I think I mentioned this before. If the expression for first derivative looks complicated, obviously you use first derivative test. If the expression for the first derivative is not so complex, meaning, okay, you still can differentiate much simpler, then of course you use second derivative test. Okay, then you just substitute the stationary point, the value, the x value of the stationary point into your second derivative test. Okay, if it's positive, if d2y over dx is positive, this means your stationary point is at its minimum. If the second derivative is negative, sorry, positive. If the second derivative test is, just like I say, negative, right? Yeah. Okay, so if the second derivative test is positive, this means that your stationary point is minimum. Okay, so using first derivative test, you test the left and right of the stationary point. So to the left of 2, you pick any value. Here I pick 1. Then you sub into your, okay, first derivative function, okay, or your derivative function, okay, or your gradient function, which is dv dx or v prime x. You sub in, you get a positive value 60, and 60 is a positive value. Okay, next, to the right of 2, you pick any value. In this case, I pick 3, and you substitute it into your v prime x or dv dx, you get a negative value. Okay, so what does this show? To the left is increasing, to the right is decreasing. So it's like a mountain shape. Correct? This means maximum lah. So we can make our conclusion lah. Therefore, the volume of box is maximized when x equals 2, and its volume is 128 cm cube. Okay, this 128, okay, you just sub into here. Okay, because our volume of box expression is x times 12 minus 2x square, right? So you just substitute x equals 2 here. Okay, so 2 times 2, 4. Correct? 12 minus 4, 8. 8 square is 64. 64 times 2, 128. Okay, so the volume is 128 meter cube. Sorry, cm cube, not meter cube. Okay, now, as I mentioned, okay, I'll give the second derivative test. So if you take the first derivative test, you see our first derivative is what? Okay, the expression for first derivative test is this one, right? 12 minus 2x times 12 minus 6, right? So, okay, you differentiate one more time. Of course, this is not so complicated, right? Okay, of course, using a product rule, the first term you differentiate is negative 2. Then you keep the second term, okay, 12 minus 6x plus 12 minus 2x, you keep the first term, you differentiate second term is minus 6. Then you just simplify a bit, okay, expand and simplify, you will get, okay, minus 96 plus 24. Okay, this is what I mean, you see, this is what I say, okay, you differentiate the first term of the first derivative function, keep the second term, plus keep the first term of the first derivative function, differentiate the second term, then you expand and you simplify, you get 24x minus 96, or minus 96 plus 24x. Okay, then you substitute your stationary point, okay, the x value of the stationary point. In this case, the x value of stationary point is 2. So I sub in, okay, minus 96 plus 24 times 2. This is a negative value. So when the second derivative is negative, what does this tell us? Basically, it tells us that, okay, the maximum volume will occur at x equals to 2 cm. Okay? And the last part of the question, they ask, find its maximum volume, right? So you just substitute x equals to 2 into the volume of the box. Okay, the expression that you derive from the wordy question. Okay? Just substitute x equals to 2, you get 128 cm cube. Okay? So this is how you use the second derivative test and how you make conclusion. Clear? Okay, I move on to problem 4. Okay, a wire of length 25 meters is to be cut into 2 pieces. Okay, wait, let me underline the keywords. Okay. Okay, so we have a wire of length 25 meters cut into 2 pieces. One of the wire is made into a square, the other into a circle. Okay, what should be the length of the 2 pieces so that the combined area of the square and circle is minimum? Okay, so assuming, okay, I have a wire, okay, and the length is 25 okay, meter. Okay, and if one side is x, okay, the remainder will be the total length of the wire, which is 25, minus the x, right? So this balance will be 25 minus x. Okay, this is the idea. Okay, so let me rub off first. Okay, let me go back to my laser pointer. Okay, so okay, the first thing first is to take note. Okay, that's not that diagram I draw. Okay, so okay, of course you define. So let the wire be cut into 2 pieces of length be x meter and 25x meter. So the first statement is what I just drew just now. Okay, the so-called the number line. Okay, which represent the length of the wire, and then the length of the wire is 25 meter. Okay, then if one side is x, the balance should be 25 minus x. Okay, now so okay, then you realize that I use, okay, I say this statement, right, then the perimeter of square is x meter, right? Why is it perimeter? Because, okay, our aim is to find, okay, the length of the two pieces, meaning the x and the 25 minus x, such that the combined area of square and the circle is minimized, or the combined area of the square and the circle is at its minimum. Okay, so in order for us to find the total area of the square and circle when it's minimized, okay, first we need to work out, okay, the perimeter. Okay, and we know perimeter of square is just the border, the outline, correct? And the first piece of wire, okay, like what the question say, the second statement, one of the wire is to be made into a square. So meaning the x meter, okay, the entire x meter, I take it to create a square. Okay, and a square has what? Basically 4 lines, right? Correct? So the x meter is basically used to create the square. Okay, hence, okay, the border of the square, which is equivalent to the perimeter of square, is x meter. Okay, like side 1 plus side 2 plus side 3 plus side 4, okay, equals to x. Okay, hence, what is one side of the square, or each side of the square? Isn't it the perimeter, total perimeter divided by 4, because square has 4 sides, correct? So, okay, that's why I have this. The side of the square is x over 4. Okay, then, in order to find, okay, because your area of circle, okay, by definition is what? Pi r square, correct? So, and I need to know what is r, correct? In order for me to substitute into the area of circle. So, I need to make use of my circumference, okay, or equivalently the perimeter of circle. But we don't use the term perimeter. Usually perimeter is for square or rectangle. So for circle, we will use an equivalent word for perimeter, which is circumference. Okay, which also stands for the border, but circumference is used for circle. Okay, so we need to make use of the circumference of the circle, which is 2 pi r equals to 25 minus x. Okay, because they tell you, right, the other part of the wire is made into a circle. Correct? So, and in order for us, okay, to utilize the definition of area of circle, okay, where area of circle there's a r there, right, pi r square, correct? We need to make use of your circumference formula. And then from the circumference formula, we make r the subject, then we substitute into your area of circle. So 2 pi r equals to 25 minus x. So you make r the subject, you have this 25 minus over 2 pi. This, okay, will be substituted into your area of circle, which I will show in the next step. Okay, clear? Your area of square will be what? L times L. Okay, and okay, which is x over 4 times x over 4, or simply x over 4 whole thing square. Okay, so the total area or the combined area of the square and circle will be L square plus pi r square. Okay, so this part is L square, this part is pi r square. Okay, like what I mentioned. Okay, so in your pi r square formula, the r here, we need to make use of your circumference of the circle, so that we make r the subject, and then we substitute here. Clear? Then you do a bit of simplification. X over 4 square is x square over 16. Then this power 2 you bring in using your properties of indices from E math. Okay, you bring in the numerator will be 25 minus x square. The denominator will be 4 pi square. Okay, then there's a pi outside, right? So pi divided by 4 pi square, that is 1 over 4 pi. Okay, that's why you see my denominator is 1 over 4 pi. Clear? So once we have this, we can find out the total area, okay, such that it is minimum. Okay, hence we will be able to find the length of the two pieces. Okay, so okay, I write down our A again here. Okay, so you take this, you differentiate the area with respect to x. Okay, so by the way, x squared over 16 is the same as 1 over 16 times x squared. I can take out the constant. Okay, then the variable, which is x squared, okay, I leave, okay, like that. Okay, same thing, 1 over 4 pi is constant, I can take it out, then I left 25 minus x squared. Okay, then all I need to do is differentiate the area with respect to x. Okay, so of course 1 over 16 is a constant, correct? Then differentiating x squared using your power rule, you bring down the 2 and then subtract 1 from the power, so that is 2x. Okay, then multiplying with the constant 1 over 16, you get 2x over 16. Okay, for this one, okay, differentiating 25 minus x squared, okay, bring down the power 2. Okay, then you have 25 minus x in front, reduce the power by 1, and then you differentiate the term inside the bracket, which is minus x. You differentiate with respect to x, you have minus 1. That's why there's a negative sign here. Okay, this negative sign is your negative 1. Okay, it comes from, okay, the term inside the bracket. Okay, then you simplify everything together, you get x over 8 minus 25 minus x over 2 pi. Okay, then from here you find the stationary value. Okay, so for stationary value, dA over dx equal to 0. Okay, then you solve. Okay, for x, so your x is 100 and 100 divided by 4 plus pi, which is approximately 14 meter. Okay, so same thing. Okay, to deduce the combined area is minimized. Okay, we use first second derivative test. Okay, first or second derivative test. Okay, to make our conclusion. Okay, so again, first I'll use first derivative test. Okay, so to the left of 14, I pick any value. In this case, I take 13. Okay, and then I substitute into my dA over dx or a prime x. Okay, by the way, dA over dx is the same as a prime x. They are the same notation. Okay, so you substitute into a dA over dx, okay, or a prime x. Okay, you get a negative value, correct? Similarly, to the right of 14, you take any value. In this case, I take 15. Okay, you can take 16 also. Okay, that should result in a positive value. Okay, so in this case, I pick 15, I sub into dA over dx, I get a positive value, 0.03345. Correct? So, to the left of 14, positive. Sorry, negative. Okay, to the right of 14, positive. Correct? So, you have what? Like a V shape. Correct? So, this implies that x equals to 14, okay, is the minimum. Okay, so this is your conclusion. Combined area is minimized. Okay, so this is how you make your conclusion. Okay, combined area is minimized when x equals to 14 and length of two pieces are 14 meter and 11 meter respectively. Okay, so okay, this part length of two pieces is basically the first part of the question. They ask what should be the length of two pieces, correct? So initially, okay, based on the diagram I drew just now, correct? Total length of the wire is 25 meter. Correct? You chop half of it to be x, the other half 25 minus x. So of course your x is 14. Then the balance is 25 minus 14, which is 11. Okay? So that's the answer. Clear? Okay, now using second derivative test. Okay, using second derivative test. Okay, wait, it's a bit lagging. Okay, yeah, so this is our dA over dx or a prime x. So you differentiate one more time, a double prime x or d2a over dx squared. Okay, you get 1 over 8 plus 1 over 2 pi. Okay, and you realize that this is a positive value. Okay, so this implies that the area is minimum. Okay, likewise, when the second derivative is negative, okay, then okay, it is okay, the stationary point is occurring at its maximum. Okay, that is for negative. But in this case, our second derivative is positive. Okay, and you see why I don't sub in the stationary value, which is x equal to 14, because once you differentiate another time, okay, from your first derivative test, okay, first derivative function, you realize that you get a constant. There is no x. Correct? There is no x. So that is why, okay, I never sub in my x equal to 14 into my a double prime x. Okay, because what I get after I differentiating from a prime x is just a constant. And from this constant, I can see that it's a positive value. Okay, you plug into your calculator, 1 over a plus 1 over 2 pi, okay, is a positive value. Okay, so I can straight away make my, okay, conclusion. Okay, so area is minimum. Okay, then you find the length of two pieces. So this part is the same as the previous part. Okay, x equal to 14 and 25 minus 14, which is 11 meter, respectively. Okay, last problem. A closed right circular cylinder has a volume of 2,156 unit cubic, okay, or cubic unit. What should be the radius of its base so that its total surface area may be minimum? So here you need to recall two formula. First, volume of cylinder. Second, total surface area or TSA of cylinder. Okay. So, but before that, okay, before I tell you the formula of the volume of cylinder, in fact, closed cylinder, and the formula for total surface area of cylinder. First, our objective or our goal here is we want to find the radii or radius, okay, plural, of the base so that the total surface area is minimized, okay, from the volume of cylinder. Okay, because why? Okay, you look at the question. The question is like that, right? What should be the radius of the base such that the total surface area is minimized or maybe minimum? Correct? That is what the question is asking you. Okay, so our goal is we want to find the radii or radius of the base so that the total surface area is minimized. Okay, so from the volume of cylinder, by definition, we know that is equivalent to pi r square h. And this pi r square h is equals to 2156. They give you, correct, unit cube. Okay, so pi r square h equals to 2156 unit cube. Okay, and you know that the volume of cylinder, you have two parameters, r and h, where r is your radius of cylinder and h the height of cylinder. So whether or not to make r the subject or h the subject from your volume of cylinder, you look at the question. We want to minimize the total surface area of the cylinder such that we want to find the radius, which means from your volume of cylinder, you should make h the subject, because if you make h the subject, then your h will be in terms of r, correct? Okay, then you can find dA over dr. Okay, dA over dr, okay, where a is the surface area, okay, of the cylinder, okay, and not dA over dh, because if you make r the subject from your volume of cylinder, then your r will be in terms of h. Then you are not answering the question. The question is asking what should be the radius of the base so that the total surface area may be minimum. So from your volume of cylinder, pi r square h, okay, equals to 2156, you should make h the subject, so your h will be in terms of r, so that later on, okay, once you have your area of cylinder, you can find dA over dr. Okay, differentiate the area with respect to r and not dA over dh, because that is not what the question wants. The question wants the radius, not height. Okay, so you need to read carefully and be careful. Okay, so that is why, okay, the second part of the statement. Okay, we will make h the subject and substitute it into the total surface area of cylinder. Okay, so first recall that the volume of cylinder is given to be pi r square h, okay, which is this they give you. Then like what I say, you make h the subject, so your h will be in terms of r. Okay, so you just bring pi r square to the other side, or equivalently divide pi r square on both sides, you get this expression. Okay, and recall the surface area of cylinder is given by 2 pi r h plus 2 pi r square. Okay, so your h, okay, sorry, I think okay, sorry. Okay, your h, okay, you replace by this guy here, okay, which is this step. Okay, 2156 over pi r square. Okay, and then you do a simplification. This pi can cancel, right? This r can cancel. Okay, then 2 times 2156 is 4312 divided by 1 factor of r in the denominator. Okay, then this will be 2 pi r square. You write back. Clear? Now you can find the, okay, now you can differentiate the area of the cylinder, closed cylinder, okay, with respect to r, because that is what you want to find, correct? What should be the radius of the base? Okay, so I think you saw the answer already. Last time I just flash out. Okay, yeah, so now you can find your dA/dr. Okay, so differentiating the area of, okay, or surface area of the closed cylinder with respect to radius. Okay, this is what, 4312 times r to the power of minus 1, right? Okay, so you use your power rule, you bring down the negative 1, you have minus 4312 times r to the power of minus 2. Okay, or equivalently minus 4312 over r square. Okay, then this one, bring the 2 down and then reduce the power by 1. So you have 2 times 2, 4 pi r. Okay, so this is the dA over dr expression. Okay, sorry, this side. Okay, then to find stationary point, dA/dr equal to 0. Okay, meaning you solve for r lah. Okay, so solving for r, you get 7 units. Okay, then the next step is to use first or second derivative test to deduce that the total surface area of the closed cylinder is minimized. Okay, so okay, for first derivative test, you test the left side of the stationary point. In this case, it's r equals 7. So I take any value. Example, I take 6. You sub into your dA over dr, you get a negative value. Okay, now for the right side of the stationary point, okay, I take any value. Example, I take 8. You sub into your dA over dr, you get a positive value. So to the left of the stationary point is negative, right, which means decreasing. To the right is increasing, which means positive. So you get a V shape, correct? So what does this mean? Minimum lah. Okay, so you can make your conclusion. Total surface area is minimized when the radius or radii of the base is 7 units. Okay. Similarly, okay, using second derivative test, okay, you differentiate one more time. So, okay, our first derivative is what? Minus 4312 over r square, right? Plus 4 pi r, correct? So you differentiate again, you should get this 8624 over r cubed plus 4 pi. Okay, then for second derivative test, it's very easy to use. Okay, you just directly sub in the stationary point, which is 7, r equals to 7. You substitute into the d2a over dr square. okay, and you realize that this is a positive value, or you just plug in your calculator. It says 24 over 7 cube plus 4 pi. Okay, your calculator should give you a result of positive value. So positive means, so when the second derivative is positive means the total surface area is minimized when r equals to 7 units. Clear? Okay, so that is all for question 3 to question 5 lah. Okay, so it's a short lesson. Okay, I know I speak a bit fast, okay, but at any point of time you can pause the recording, okay, and okay, take down your own notes, okay, as well as the solution, okay, if there's any errors in your own solution, okay, feel free to pause the recording, okay, yeah, okay, and yeah, I also start a bit of integration techniques, okay, but I haven't really go into the question, okay, just basically go through some rules of integration, okay, like for differentiation you have some rules like constant multiple rule, power rule, factor rule, okay, product rule, quotient rule, chain rule, right? For integration we also have rules of integrations, okay, so that, okay, or what we call it techniques of the integration, okay, so that is to bring me to the next slide. So for our techniques of integration, okay, or integration in short, okay, is actually the reverse process of differentiation, okay, integration is the reverse process of integration. So what I mean is, if you see, okay, for look, notice, okay, when you differentiate x to the n, what you do? You bring down the power n and times x power minus 1, correct? Correct or not? N times x, okay, to the power of n minus 1, correct? Okay, so for integration, okay, how you integrate, okay, a value raised to the power of n, okay, basically you add the power by 1 and you decrease the power by 1, so you increase the power by 1 and you divide by the power plus 1, so x to the n plus 1 divide n plus 1, then for integration, there is always a plus c. This plus c is your arbitrary constant of integration, okay, and there's one important thing to note, okay, because you see, when you increase the power by 1 and you divide by the power by 1, right, okay, notice that, okay, n plus 1 cannot be 0, okay, and for n plus 1 cannot be 0, the value of n cannot be minus 1, because what happens if n is minus 1? Then the denominator is 0, which is undefined, okay, so this is an important constraint to take note, okay, and then you can see this thing that I put, because, okay, this inverted triangle is because short form notation in mathematics, okay, so because, okay, the derivative of, so basically you see, the integral of x to the n is x to the n plus 1 divided by n plus 1 plus c, right? Right? So likewise, the derivative of the right hand side is the left hand side. That's why you see, okay, inside the parentheses, okay, when I differentiate this, correct, okay, I should get back x to the n. Okay, you look at the right hand side, x to the n, correct? So when I differentiate this, I should get back x to the n. So first, okay, from your power rule of differentiation, we know that, okay, we need to bring down the power, reduce the power by 1, right? So you do that, n plus 1 you bring down, that's why you see there's n plus 1 in front of x, correct? Then you reduce the power by 1, okay? So you bring down the power n plus 1, then you reduce by 1, so n plus 1 minus 1, okay, then divided by the n plus 1, which is by there, okay, by default, okay, then after that, do some simplification, cancel out the n plus 1, and then in the power of x, you'll notice that n plus 1 minus 1, the 1 minus 1 will vanish, so you just left n, hence you get x to the n, okay? So what I'm trying to say here is, okay, the integral of x to the n with respect to x is x to the n plus 1 divided by n plus 1 plus c, okay? Likewise, the derivative of the right hand side is the left hand side, okay, like what I showed to you here, okay? That's why it's called reverse process of differentiation, okay? It's like working backwards, okay, like what Charlie mentioned in the class today, okay, you can think of integration as the backward process of differentiation, okay, you work backwards, okay. Then for second one, notice for differentiation, when you differentiate a constant, you always get 0, correct? However, when you integrate a constant with respect to x, that is not 0, that is just the constant times x, which is ax plus c, okay? Next, what happens if you have a constant times a function? So this function can be a family of polynomials of degree 1, 2, 3, so on and so forth, okay? So what happens if we have that, a constant times a function? So since the constant doesn't depend on x, it's just a number, correct? A is just a number, correct? Okay, so I can move out of the integrand, okay? And then I integrate f of x, okay? Notice here I use small f, here I use capital F, because why? When I integrate small f, okay, this will become capital F, okay? Where capital F of x is the antiderivative of f of x. Antiderivative means integration, okay? Like you take away the word anti, you get derivative, right? So what is the opposite of derivative? Antiderivative lah, which means integral, okay? Clear? So f of x is the antiderivative of f of x. Okay, so here I use capital F, so that not to confuse with this. Okay, so instead of writing a times small f of x, I write a times capital F. So this capital F is your antiderivative of small f. Okay, the small f is, okay, the function. So when you integrate, it's capital F. Okay? And then don't forget your constant of integration plus c. Okay, by the way, I missed out. Then the notation for integral is this wavy sign. This one. Okay? Okay, or maybe let me rewrite. Okay. Okay, that is the notation for, okay, integrate. Like that. Okay, some wavy symbol. Clear? No, okay, moving on. The third point. Okay. Okay, the integral of u plus v plus w, or u minus v minus w, is the respective integral. Okay, so basically you can think of this like term by term. You integrate term by term. Okay. Yeah. Okay, or okay, there's another way of saying the integrand of the sum is the sum of the integrand. Okay. Can if you don't understand what is the integral of the sum is the sum of the integrand, basically term by term integration. Okay. Okay. Next one, if you have a, let's say, a linear expression raised to the nth power, what you do is, okay, actually part 5 is the same as part 1. Okay, the only thing is you divide by the coefficient of x. Okay, you notice you increase the power by 1, which is same as the first point, right? Correct? Correct? Ax plus b to the power of n plus 1, then you divide by the power by 1, correct? And then there's an additional a in front in your denominator, correct? Basically, increase the power by 1 and divide by the power by 1, and then don't forget to divide by the coefficient of x, because we are integrating with respect to x. Okay? Yeah. Clear? And you can see here, okay, under the because, okay, like what I mentioned, the integrand of this is this result, correct? So if you work backwards, okay, you differentiate this ax plus b to the power of n plus 1 divided by a times n plus 1, I should get ax plus b to the n. Okay, so clear enough, you can see I do here for you. Okay, first you bring down the power, okay, and then inside the bracket remain the same, okay, and then power reduced by 1, so we have n plus 1 minus 1. Then differentiate the term inside the bracket, okay, your chain rule, which is a, okay. Then the a and the n plus 1 in the numerator you copy back. Then you see that, okay, you see what? Then you see this n plus 1 and this n plus 1 can cancel, correct? This a and this a can cancel, and in the power of ax plus b, the 1 minus 1 vanishes. So that's why you have ax plus b. And isn't this the same as this? Correct? So that's why integration is called the reverse process of differentiation. Okay? And because we know that the derivative of ln x is 1 over x, right? So the integral of 1 over x is ln x. Okay? And don't forget your constant integration plus c. Okay? Okay, so for trigonometry, okay, we know that the derivative of cosine x is minus sine x, right? So the integral of sine x is just negative cosine x plus c. Okay? Likewise for cosine x. Okay, we know that the derivative of sine x is cosine x. So the integrand of cosine x is sine x. Okay? For tangent, we know that the derivative of tangent x, okay, which is sine over cosine. Then you use your quotient rule, you get secant square x. Okay, use your quotient rule and simplify, you get secant square x. Okay, so the derivative of tangent x is secant square x. So if you integrate secant square x, okay, you get tangent x. Okay, of course you have a plus c. Okay, then for exponential function e to the x, and notice e to the x is always positive. E to the x is always a positive function. Okay, clear? Okay, the derivative of e to the x is e to the x. Okay, so the integral of e to the x is e to the x. Okay, so these are some okay, I call it rules of integration. Actually, okay, in the handout, chapter 11 is all there. Okay, I think Charlene has the handout already. Okay, but please remember to bring the next session. Okay, on 11 April. Okay, don't forget to bring. Okay, for Jia your handout is in the center. Okay, yeah, so, okay, so anyway, all these rule of integration is actually in the handout. Okay, so with this being explained, okay, I have some assignment for you to do lah. Okay, actually I seldom give my students assignment on. Okay, but if I have to, then usually it's a very simple assignment. Okay, so the assignment is the next page. Okay, try out exercise 1. Okay, so for Jia, you don't have the handout. Okay, I'll give you the e-copy inside the Telegram group, so you can refer to the e-copy inside the Telegram group. Then you can write down a solution of a piece of paper first. And next week, okay, when you receive the actual handout, okay, you can just transfer over, okay, your solutions onto the handout. Okay, so assignment, try exercise 1. Okay, using, okay, these rules of integration, okay, that I've explained here. Okay, basically integration is the reverse process of differentiation, or like what Charlene say, okay, working backwards. Okay, from differentiation you work backwards, you get integration. Okay, just like algebra, expansion and factorization. Okay, when you expand two or more algebraic term, okay, you get one chunk of expression, right? Correct? Then, okay, then from that chunk of expression, okay, when you factorize out, you should get back product of two linear terms. Okay, so it's similar to expand and factorize. Okay, it's like reverse process. Expand and factorize are reverse process. So in calculus, differentiation and integration are reverse process of each other. Okay, so you can think of that way. Clear? Okay, if not, yeah, I conclude the session. Okay, so total is about 41 minutes lah. Okay, so yeah. Okay, see you the next lesson. Okay, bye bye.